Welcome today to following Perseverance rover. Very exciting to Mars, our next rover. And I'm Carter Emard. I'm the Director of Astrovisualization at the American Museum of Natural History. And we're thrilled today to be bringing you this program where we're going to visualize using a tool called OpenSpace that will allow us to get right down to the surface of Mars, show you how we actually go from Earth to Mars. But we're doing this in collaboration with three Mars scientists, and I want them to introduce themselves. And so our first scientist is Dr. Kenda Lynch. Kenda?
Hi, everyone. My name is Kenda Lynch, and I am a staff scientist at the Lunar and Planetary Institute here in Houston, Texas. And I'm an astrobiologist and a geomicrobiologist. So what I do is I study life here on Earth and try to understand all the amazing extreme environments that life can live in here on Earth and how they live there and how they can leave signs that they were once there so that we can use that information to learn how to look for life on other planets. And in particular, I study paleo lakes on Earth to learn how to look for life in paleo lakes on Mars.
Well, thank you, Kenda. And we also have Dr. Liz Rampey from NASA. Liz.
Yeah, thanks, Carter. Yeah, so my name is Liz Rampey, and I'm a planetary scientist at the NASA Johnson Space Center in Houston, Texas. I'm a Mars geologist, and I study the minerals on the Martian surface that form from water-rock interactions. So we know that Mars once had abundant liquid water on its surface about 3 to 4 billion years ago, based on evidence for lakes and rivers and groundwater. And the minerals that we find in those deposits can tell us a lot more about what those waters were like. So some minerals can tell us if the waters were fresh or salty, acidic or basic, or warm or cool. And I study these minerals on the Martian surface using data that are collected by the Mars Science Laboratory Curiosity rover, which landed in Gale Crater in August 2012 and is still operating today. I also study minerals in places on Earth that we think are similar to or analogous to Mars 3 or 4 billion years ago. So I do field work in places like Iceland, Hawaii, and the Cascades of Oregon. And so I collect rocks and sediments from those locations and study them using instruments in our laboratories at NASA that are similar to instruments that are on missions on Mars, so that we can try to identify these minerals from data that come from Mars.
Well, thank you, Liz. And also we have Dr. Germán Martinez, who is an atmospheric scientist. Germán, can you introduce yourself, please?
Yeah. Hi, everyone. My big pleasure to be here with you. So this is Germán Martinez. I'm a planetary scientist, a staff scientist at the Lunar and Planetary Institute down in Texas. And in short, to make it simple, I'm a Martian weatherman. I'm part of the Mars Science Laboratory Curiosity rover, where I am analyzing data from the weather station called REMS. And I am also co-principal investigator on the Mars 20 and 20 mission, the Perseverance rover, where I will also be analyzing meteorological data from a weather station called MEDA. And if you are wondering why we need a weatherman on Mars, you might be thinking, well, it doesn't rain on Mars, it doesn't rain water. That is true, guys, but it snows and there are big dust storms. And at some point, crewed missions will go to Mars, maybe in the next decade. And to ensure the safety of our astronauts, we will need to be able to predict dust storms. We will be able to predict the weather on Mars to, again, ensure the safety of our future people going to Mars.
Thank you, Germán. And I want to emphasize that right now in our YouTube chat, we have basically a place for you to ask questions. And so our three notable scientists here will be answering questions. I'm going to give a bit of an intro on how we are going to send Perseverance to Mars. I'm going to be joined in a way, but silently, by Micah Ajnapura, who's a developer for open space at the museum with us. And but he will be our pilot. So if I'm talking to Micah, and he will be actually guiding this live. OpenSpace is an interactive data visualization tool, and that means that what we show you is all real information. If you're interested in downloading OpenSpace for yourself, you can do that at openspaceproject.com, and our team members are also in the chat if you're interested and want to download that yourself. So I think what we'd like to do now is go to the visualization. We're going to see the sun in the middle of the screen. We can see the constellation Orion off to the left of the three prominent belt stars, but we can also see the orbits, the trails of the four inner planets of the solar system. Closest to the sun, Mercury, next out, Venus. Third planet from the sun, of course, is Earth, and then the fourth planet, next planet out, is Mars. And Mars is interesting. You notice how the trails are such that we all go around the sun. And the closer we are to the gravity source, the faster we go. So Mercury goes around in 88 days. It takes us 1 year. Mars, almost 2 years. To launch to Mars, we have to wait for the planets to align. And that really is the case. We have to produce, basically a spacecraft in time and a schedule to launch very specifically. That comes up just about every 2 years. Then there's a narrow, what we call a launch window. So I'm going to ask Micah if we can come in a little closer. What I want to do is enlarge Earth and Mars. We're enlarging them by a factor of 3,000. What you're seeing when we see these trails, we're to see the inner solar system, we have to back away. The planets are just not even visible. They're sort of stellar-like apparitions, like when you look up in the sky and maybe see Venus or see Mars as we're approaching it now. So Earth is twice the size of Mars. We're the blue planet, and Mars is the red planet. And Mars has had a rich history in our observations telescopically. We can see that it had seasons. We can see it rotates almost the same day as Earth. It's about a half hour longer. And right here, we're showing where Earth and Mars are, and we're now going to run time lapse. And as we do, I'm going to ask Micah to shrink the planets back down to size, because what we'll be seeing is the trail of Perseverance once it's launched on its Delta V launch vehicle from Kennedy Space Center, set for late next month, July, and the launch window is between July 22nd and August 11th. As we run time faster, so we're going to go across about 7 months here. We're going from July all the way to February of next year. Regardless of the day that we actually launch, that we will reach Mars as planned on February 18th of 2021. And so here you can see between Earth is actually passing Mars. It goes around faster, it goes around 1 year. Mars about almost 2 years for one orbit. And it's almost as though we hand off the spacecraft that goes out to Mars. But that arc, that orbit that goes out, it's called a Hohmann transfer orbit, and it's aimed to where Mars will be. And so we aim exactly to sort of where Mars will be. And so at this point, it's sort of between Earth and Mars, but it kind of leads out in front of Mars. As it does, it starts to sort of slow down with relation to Mars, and Mars comes up and overtakes it. So we have this plan so that we're going to switch the view from where we're seeing basically the trails of everything with respect to the sun to that of Mars itself. So we're going to see the spacecraft. In this case, we call it an aeroshell. It's basically a safe enclosure for Perseverance rover that is traveling through space, and it has communications equipment and all that, but is now sort of reaching out to where it begins to feel the gravity of Mars, and it starts falling into Mars. So we see this trail sort of bombing in directly at Mars. And notice how Mars has two companions. These are its moons. We have, of course, just one moon, our moon, but Mars has two. So Mars being, once again, about half the size of Earth, it has two moons that are almost like asteroids or much smaller than our moon. And here we are, we're coming in. As we get closer, we're going to slow down. Notice how already we can see this line is not aimed directly at Mars. That might make, we don't want to do that. We want to aim very, very carefully right for its atmosphere. And the timing has to be just right. You notice how Mars is rotating there. And the feature that we're aiming at is just slightly east of feature that has been seen on Earth almost 350 years. Christian Huygens was the first to actually draw it, and it's called Syrtis Major. We now know that it's the darkest feature on Mars, but it's also sort of the edifice of a large volcano. And at the edge of it is a crater called Jezero, and that's where we're targeting. Notice how all the craters kind of look like the moon. These are asteroidal impacts, craters of various sizes, but also notice how Mars has this atmosphere and it's red in color. So it's similar to the moon with its craters, but having an atmosphere, it's kind of Earth-like. It's twice the size of our moon, but half the size of our Earth. It's sort of caught between sort of Earth and the moon in a sense. So what's happening here, Micah's slowing us down, swinging to the side a little bit. We'll see how the orbit, I'm going to ask Micah to come a little bit lower inclination here so that, yeah, we bring the horizon down a little bit, that when it encounters the atmosphere, it has a heat shield, and that's going to slow it down. And it begins to sort of level out in the atmosphere, slowing down, slowing down. This is what has been called 7 minutes of terror. The design of the Perseverance rover is very similar, has just different instruments on it, but very similar to Curiosity, which Liz mentioned in her introduction, landed in 2012 and successfully. And so we're building hopefully off that success for the landing of this rover in a similar type. Mike is looking back so that we can see here's the incoming trajectory. This is a trajectory described mathematically by NASA. And we're using that to visualize and draw this line. This is not just an artistic illustration, it's actually what is actually happening. The map we're flying over is this real map of Mars. It's been photographed by Mars Reconnaissance Orbiter, pieced together into this large map. The atmosphere is accurate. It's the proper scattering model. It's a mathematical model of the atmosphere. And so as we come in, we're gliding over and slowing down, but it's popped off a parachute. We're not going to show you that. I'll show you that in the diagram, but we're going to come closer now. What I want Micah to do is come in for this final approach. We're flying over landscape that is cratered, but also the cratering's been modified by streams, river valleys, and where we're targeting in Jezero Crater is a delta. And what we can see is a delta, just like deltas on Earth. This is where a stream basically comes out and enters into a body of water. So we believe the Jezero Crater was a lake. You'll notice that in the imagery, we have this overall map, but now we see some higher resolution images, these high-rise images that get down to below 1 meter in resolution. And also notice there's a height model. So we've done analysis on the images so that we have an accurate elevation model of all of this. All of this goes into the calculations. And for the first time, Perseverance actually has an optical navigation system where it has a map on board, and it will compare images that it's taking on descent for obstacle avoidance. That is the delta directly below us. Micah, can you actually look down? We're swinging around the position of where the rover is. We'll look down and actually see the delta, and then we'll see the details of this. So these sort of cliff walls at the edge is where the delta ends. And then this pitted area in front of us is really this level area. This is very important for us to land in a geologically interesting area. There are many points of Mars that are very geologically interesting, but they might be too challenging to actually land on. So Micah, in the last minute here, I think we're descending actually on the actual trajectory. The parachute has slowed it down, and it's on a final vertical descent. At a certain point around here, the parachute is cut loose. You might think, well, a parachute might not bring the rover in with that. The atmosphere on Mars is about 1% as thick as the atmosphere on Earth. And it deceptively kind of looks thicker, but that's because of this dust. Everyone can talk about that. But this final descent is actually on a jetpack. This is how Curiosity came in. This jetpack actually is firing its engines to basically bring Curiosity down under a cabling system, and it will hover. All of this has to be done autonomously. We're coming in just forward of these very interesting hills that we look forward to sample, and then Perseverance will come in and land. And so, lowered by the cables, it will finally cut the cables and deliver the rover gently onto the surface. The cables will be cut, the jetpack will go off and crash somewhere. So that's how we deliver a 1 ton, just over 1 ton vehicle, about the size of a Mini Cooper car, to the surface. So Micah shows here we see the rover on the surface, and so we're going to see that. And we could level off. We might see some of the terrain surrounding where the rover comes in. And over this high resolution image, as I mentioned, from the HiRISE camera, Mars Reconnaissance Orbiter. I have a few slides that I'd like to just show, so Micah can bring that up. Perseverance is actually part of a family of rovers that have gone to Mars, with each mission basically building off the success of the previous. So this is very nice. We can see the edge of the delta in the background. This is a picture of Perseverance in the assembly room at NASA's Jet Propulsion Laboratory. So you can see with one of the engineers standing next to it how big it is, and it really is the size of like a small car. Notice off the sort of back of it, between the main part of the rover and sort of angling up off its back, sort of in front of the head of the individual, there is actually its energy source. It's a nuclear battery. It's plutonium. Mars is cold and plutonium's hot. So between that, you run a thermocouple, and that generates your energy. So and then that will run the wheels and all the scientific instruments. So next slide, you see just a picture of the legacy of rovers, I believe. And in the background, once again, we're seeing some of the imagery. So I mentioned that the Perseverance is in this family of rovers. You can see that NASA's 23 years of success of putting rovers on Mars. We started with the very small Sojourner rover, named after the abolitionist Sojourner Truth. And so that was about knee-high, and that was in 1997, Mars Pathfinder. And then later, the 2 solar-powered rovers, Mars exploration rovers, Spirit and Curiosity. And so we see them. Spirit lasted for about 6 years. They were designed to last 3 months, landing in 2004, both in January of 2004. An opportunity we just lost 2 years ago in 2018. Not bad for a 14-year mission. Nobody gets better mileage than NASA. We go into extended mission phase, but then we landed the 1 ton Curiosity, and you can see how big that is. That mast that sticks up has the cameras on board, and we can see the robotic arm. The next picture shows basically how we came in, on just a diagram of that, I believe. Let's see, it comes up. Yep. And so here we can see, as I mentioned, it comes tucked into what's called an aeroshell, pops its parachute, and which sort of slows it down, levels off the flight. And then finally, the next picture, we'll see this engineering illustration of the final descent under jetpack, powered descent, to gingerly bring it in and deliver it to the surface. Oh, actually, this picture is an amazing picture of Curiosity coming in over Gale Crater in 2012. And this was taken by the orbiter, the Mars Reconnaissance Orbiter, with a HiRISE camera, capturing the parachute and Curiosity coming in under its aeroshell. So next picture actually shows just a little bit of the, let's see, wait for that for a second. Great. Okay. And so here we see, this is called the Sky Crane. So it has 4 jets splayed to the side, and it gently lowers the rover down, and the wheels will unfold, and as soon as it has a touchdown signal, it cuts the cables, the jetpack goes off and crashes. So the next picture, what's exciting about this mission, that in these series of rovers, in the investigations on Mars, that Perseverance is actually has a suite of instruments designed actually to look for traces of former life on Mars, and it also has an experiment to make oxygen, which will be needed for astronauts in the future. And actually, the Sherlock camera on the end of the mechanical arm, it also has some materials to test spacesuit material for future crews. But also there is the weather station and an array of cameras. And also it has a sounder, basically a radar to pound underneath the surface and see underneath to pick up ice and water, traces of that. So an array of very interesting instruments. But in this suite of rovers, and what NASA's been doing is to really follow this question of we see landforms on Mars and have since the early explorations of Mars going back to the early 70s, is the traces of what look like water. And our rovers and landers have actually proven that there's ice there. Mars is very cold now, but in order to have a lake, and a delta, and streams, that Mars has changed over the years. And so we've proven with Curiosity and Spirit that there were actually lakes on Mars, the water. Phoenix mission found ice up around the poles. That was just a lander. And then Curiosity was looking for the elemental abundances on Mars that would actually be potentially supporting life. And then this time with Perseverance, we go and we're actually looking for traces of life. But one other thing, the samples that it's going to collect are designed to be basically left on the surface so that they can be picked up by hopefully the next mission that will send basically a rocket to pick these. And a little rover will go out, pick up the samples, deliver them to the rocket as a sample return to Earth. This has never been done before. But there's one last thing. I'm going to go to the next picture here. Very exciting is sort of proving the technology of making oxygen on Mars. I mentioned that. That's with the MOXIE experiment. But here is the lead engineer of Ingenuity, which is the name of this cute little drone. This is a helicopter on Mars. And Mimi Ung is the lead engineer on this. And so this will unfold, be put on Mars. It rides on the belly of Perseverance. And so this is a technology test, but drones will be used most likely in the future to sort of fly up and around to actually scout Mars and look ahead. So with that, what I'd like to do is now just explore this terrain, and I want to invite our scientists in to actually speak with us about what we see. Just this last image I think I'll speak to is it shows where Perseverance is landing, but also shows these other successful landings that NASA has conducted on Mars. This is Jezero Delta. And so we see this layout in front of us. And very carefully, we're expecting to land in this flat area at the base of these hills that rise up. You might wonder, why does this delta have these hills? And that's because as the water came in, and if we can see in the background where the stream actually cut through the edge of this crater. This is an ancient crater, and I'd like to bring Liz Rampe in here, and she's a geologist, and I'd like Liz to tell us a little bit about the delta, and then we'll go from there. Liz?
Sure, yeah, thanks for asking. So deltas form anywhere that a river or stream flows into a standing body of water. So it could be a river or stream flowing into a lake. It could be a river flowing into an ocean. And those sediments that are carried by the river or stream then are deposited as that river or stream empties into this body of water. And so when we see this feature anywhere on any planet, we know what process formed it. These are fairly common in ancient craters on Mars because ancient Mars had liquid water, and these ancient craters were fairly deep, localized basins where liquid water could accumulate. And so we see evidence for these deltas and lake basins really across the ancient southern highlands of Mars.
There's a question coming in. Ben asks how hot Mars is, and I believe I mentioned at one point that Mars is very cold, but Liz, how cold is Mars?
Yeah, and actually, since we've got our weatherman, maybe could we ask Herman?
Absolutely.
Cool,
Yeah.
Herman.
So that's a very good question, because people might think that Mars is super cold, and it is. But what many people do not know is that over the course of a day, so on Mars, one day lasts also like 24 hours and 40 minutes. It's a little bit longer the day than on Earth. You might have temperatures in the, like high 60s, so that's like nice weather during the daytime. Let's say at 2 p.m., like let's say 65 Fahrenheit. That's what the InSight lander and that's what the Curiosity rover are measuring during springtime and summertime. The problem is that same day at nighttime, the temperatures go down to, I don't know, like minus 70 Fahrenheit, minus 80 Fahrenheit, and this all happens within the same day. So you are like at 1 meter high at the surface of Mars, and over the course of a day, you go from, like 70 Fahrenheit, which is nice, to extremely cold. So it's both cold and warm.
So I had another question for you, Herman, that we can kind of, we show in our atmosphere here that Mars almost, it deceptively looks like Earth because we see the atmosphere and it's just a different color, sort of pink, orange. But this color of Mars, maybe this is a question for Liz as well, but this color of red, I believe it's iron oxide, but do we know why it's there? And then Herman, how thin, there's dust, but I'm just wondering how small are the particles of dust?
I can talk about the color of the atmosphere. I'm pretty sure that Liz will love to talk about the color of the soil. But basically, the color of the atmosphere is caused by the interaction between the solar radiation and the suspended dust. So pretty much as the same way as on Earth, we have like water vapor interacting with solar radiation and creating the colors that we can see here on Earth. On Mars, those colors are caused by this dust, which has a size of about a few microns, so it's like it's micrometers, it's basically like thinner than a hair. So it's like micrometers thick.
Is that like the size of talcum powder or more like smoke?
Would be a smoke rather, I guess. Yeah, it's again, like we cannot see it. It's microscopic, and it's, let's say, like, I don't know, like 100 times or 1,000 times thinner than a piece of hair, like in our head. So definitely little.
Well, Liz, I didn't know if you had anything to add to the color for Mars.
Yeah, I can. Speaking from a mineralogist's perspective, so the red color comes from iron oxides and oxyhydroxides. So it's iron 3+ in these minerals, and those minerals are causing the red color. Modern Mars is has a fairly oxidizing surface because of UV photolysis and interaction in the atmosphere. But with Curiosity, we do have a drill to help us collect materials and analyze them with our laboratories inside the rover. And in some rocks, we actually see that this red color is just a surface veneer. And once we drill just even a few centimeters or an inch or two below the surface, we see that the surface is sometimes gray, meaning that those minerals have not been as oxidized as those on the surface.
Well, this is very interesting, and I have a number of questions for Kenda as well, because Kenda, as our astrobiologist here, this is very exciting that we've gone from essentially proving that there were lakes on Mars and that water was involved, to then the minerals associated with that could support life. But this is the first time, this isn't the first time, right, Kenda, that we've actually looked for traces of life on Mars?
Hi, actually, yeah, no, it's not the first time that we've looked for signs of life on Mars. So Perseverance's mission is to search for signs of life on Mars, or what we call biosignatures, but it is definitely not the first time that we've done that. Back in the 1970s, we sent a lander. We didn't have roving capability back then, but we could land on Mars. We sent a lander called Viking to the surface of Mars to do the same thing and look for signs of life. But back in the 1970s, we didn't have a lot of the knowledge or technology that we have now. We didn't know about extreme environments, for example. We didn't know about deep sea hydrothermal vents. We didn't know about like hydrothermophile bacteria living in Yellowstone. We didn't know about bacteria that could live on nuclear reactors. We didn't know that bacteria could live deep in the subsurface of the earth. We didn't know anything about that. We didn't know about RNA, and we didn't have the level of technology that could help us make these really, really small instruments that we use. So back then, our knowledge of life and what life could do and where life could go was very limited, and that drove the experiments that we made. And plus, our technology was also a little limited. So when we sat down on Mars and we looked at we set our instrument suite down to look at the surface and try to see if they could find anything. You know, some of our instruments said, yep, we found something. And some of our other instruments said, no, we're not really sure if we found anything, or no, we didn't. And so the response came back as, we don't know, because it was very ambiguous. We didn't have all the instruments agreeing with each other. So it was hard to say yes or no. And that kind of was one of the things that made us start to ask ourselves as scientists, well, do we really know what life is? Do we know how to look at life? And kind of kicked off the science of astrobiology, because we realized that we really needed to learn more about what does it mean to be alive? How far can life go? What are the limits that life can live at, so that we can really try to understand how to look for life and then come back and take another look. When the technology and our knowledge got to a place where we could maybe ask the question again. And we're there today, and it's so exciting to be able to send Perseverance back to Mars to be able to ask this question again.
Yes, it was very exciting, and Mike is actually now flying us down amongst these landforms that are with the delta. We can actually kind of see there's some ripples down below us. Those are actually sand dunes. Herman, we have sand dunes on Mars, and we don't have those on the moon. The moon doesn't have an atmosphere. But can you tell us about the sand dunes that we're seeing?
Yeah, sure. Yeah, it's important. I mean, the sand dunes are not just telling us about winds on current Mars, but these are indeed, like geologic landforms that created many years ago. And when I say many years, I mean like millions of years ago. And it's interesting because based on the direction of the ripples, and based on the distance between the crests of the sand dunes, those are telling us about the past of Mars. Those are telling us about the climate conditions and wind conditions in ancient Mars. So it's not just about, like current Mars, current climate. It's also telling us a lot about past Mars.
There's also in the vista that we're seeing here, and Mike is actually doing this nice job of taking us out across and looking around. The hills that we see in the background are actually the edge of the crater. I'm going to ask Micah to actually come up above and look down once again so that we can see sort of the general layout of this area. Once again, notice how there are broad flat areas, and this is sort of defined by the needs of coming in and landing. In fact, reminds me that we actually have something else that we can show here, which is called a landing ellipse, or this is sort of the probability area. We aim for Jezero Crater, but we actually have about a 10-kilometer wide. 10 kilometers, if you think in miles, I tend to think in miles, is just over 6 miles. I actually looked at this. If you've been to New York and been to our museum, and then walked all the way down to Battery Park, that's about the distance, the width of this circle that we'll see here. And that's about the size of the delta itself. The crater's bigger than that. But we are also seeing that the on top of the hills that we saw in the delta was this sort of cap rock. There's a smaller crater we see on the delta that happened after the delta formed. But here we see the edge of Jezero Crater, and see that stream up to the upper right. That's where it cut through and then presumably filled this crater, this low spot, of course, with the lake. And so I think we can come down a little closer again, Micah, but this shows basically we launch from Florida and we come in and we do our best to aim for that 10-kilometer circle. And each mission that we've sent to Mars has had a landing ellipse, sort of the zone of probability of where it's going to land within. And but these have gotten smaller and smaller. I mentioned it has an image-based, in the engineering of it has basically images that will be compared on board in real time without communicating back to Earth, basically doing this autonomously to make sure that it lands where we want it to in the flat area. And you see in the landing ellipse, it had the hills in it. But also, multispectral views from our orbiters show mineralizations. It gets us back to some questions with Liz. That I know that there's been this sort of search for a type of rock that's altered by water, and I know that was kind of elusive, but we see that here, these carbonate rocks. I wanted to ask Liz just that story of the mineral alteration of what we see of the minerals from orbit, and then this dust that Herman was just talking about covering over all that. And so I first want to just ask Liz just about what we see across this delta and what sort of chemical signatures we might find interesting from orbit.
That's a great question. So from orbit, we see a variety of different minerals within the delta and also on the plains of the crater. On the plains of the crater, we see signatures of igneous minerals because there are ancient lava flows that have partially infilled the crater. And so we see minerals like olivine, which is common in basalt. It's that bright green mineral. And if any of you have been or were born in August, olivine or peridot is your birthstone. I was born in August. But other mineral signatures we see are things like clay minerals and, like you said, carbonates. And when we see these minerals, we know that they formed in the presence of liquid water, which is huge, very important. In terms of carbonates, this is a really interesting finding because they are not very common on Mars, even though the atmosphere is dominated by CO2, and we see a lot of carbonates on the surface of Earth. So one hypothesis is that these carbonates on Mars might have precipitated when the Martian atmosphere was a little thicker, there was more CO2 in the atmosphere, and maybe during a time when Mars would have been habitable. And Carter, you talked about the dust and how it really affects what we can see from the surface, and that is absolutely right. We see this with Curiosity, where we landed in Gale Crater because we saw some specific units that had clay minerals and sulfates. We couldn't land on those specifically because they were not safe to land on. They were on these sort of steep slopes. So we landed out in the plains of Gale Crater, but we saw some of those minerals that we could not detect from orbit because of the dust cover out on the plains too. And so I expect once Perseverance gets on the ground, we will see a variety of minerals that we could not have seen from orbit.
Very interesting, and this chemistry aspect of life and the search for life is a delicate question. I just wanted to point out that we have the experts here, but it's just that. Well, first I'll ask Liz, how old is this crater, and how does that relate, for Kenda, sort of to the timescale of life on Earth, or the earliest life we know of on Earth?
Yeah, I'll take the age of the crater. It's about 3.8 billion years old. So it's really in that sweet spot on Mars, about 3.5 to 4 billion years ago, when we think that there was abundant liquid water on the surface, lakes, rivers, streams, and groundwater. Kenda?
And then just remind me, the question is, what does that mean for life on Earth at that same time?
Oh, I was wondering, kind of, we go to Mars, and we see evidence for of water, but that Mars changed. That's another question, of course. Mm-hmm. But that in the ancient past, Mars seems to have had water. And so that we're going and looking for, are we looking for life, or are we looking for traces of life? And how does that relate to, because this is very old, what life was like on Earth back then?
So what we're looking for is biosignatures, which are not necessarily traces, but they're evidence that life was there. And biosignatures can be a whole host of different things. They can be actual biologically made material, like we can look for lipids and amino acids and different types of organics that were made exclusively that we know on Earth by biology. But it can also be things like different textures and fabrics in the rock, like different structures in the rock that most likely were made by biology. We can also look chemically at the rocks and see if there's any evidence that life was once there. Life tends to like to concentrate things. So if we can look at the rocks, and we can look at certain concentrations of certain types of elements versus others, that could also be a biosignature and an indication that life was once there. And the good thing is we do have a lot of things that can survive geological time. We have biological material that can last for up to billions of years, that can get preserved into the rock, that we study here on Earth, and we know that it can survive a long time. So. And the age of the crater and the age of Mars, back about 3.5 billion years ago, 4 billion years ago, that's exactly when life was starting to emerge on Earth anyway. So it's quite possible for life to have been also possibly emerging or actively going on Mars at about the same time.
Well, this brings up this question of change, and I'd like to ask Herman that. That if we have this atmosphere and what we know about it, explore it. We have weather stations, Curiosity. We're sending another one, Perseverance. So how did Mars change? I mean, how did it go from being, a warmer and wetter climate to the thicker atmosphere to allow liquid water? And what's the story here? How did it change? Do we know?
That's the $1 million question. Honestly, we are not sure about it yet. There's this NASA orbiter called MAVEN, which is a study, what happened to the atmospheric water on Mars, why did it escape, So basically, there are a couple of hypotheses, There are some scientists that said that Mars in the past was warm and wet, so pretty much like on Earth. And that it would have an ocean in the northern hemisphere of Mars, so pretty much like half of Mars would host an ocean. There's these different hypotheses that said, or that says that, no, in the past Mars was not wet and warm, it was still dry and icy, but basically, like the meltdown from the ice in the southern hemisphere, like created this liquid water. So in other words, we are not sure yet. The Perseverance rover will have instrumentation that will greatly help us, find out this past climate of Mars. We have also this orbiter Maven telling us a lot about it, but as of now, we don't know. That's a great question, and that's what a lot of scientists are working on.
So there's a question that Bijal asks. Does Mars? This is a question really for Kenda. Does Mars have water? Like today, and what would that mean for possible life on Mars?
That is that is actually a very, very good question. So yes, the answer is Mars absolutely has water still on the planet today, but at the surface of Mars and in the near subsurface, most of that water is frozen. So it's frozen at it's in our polar caps. It's frozen as ice, and it's also permafrost. And there is also liquid water absorbed into all of our aqueous minerals. Our aqueous minerals are that because they actually integrate water into the minerals. So we do have water all over the planet, but it's captured in multiple different ways. So the question of whether or not we still have liquid water, if we have a large amount of liquid water, it would be really, really deep in the subsurface, and we don't know that yet. We think it could be there, but we don't have definitive evidence of that. There's been some detections, but we're still working on the science of that. In the near subsurface, we know that sometimes we get what's called metastable or transient liquid water that can happen. But it's very short-lived, and it's very, very cold, and it's actually extremely, extremely salty, because that's the only way we can get liquid water kind of in the near subsurface or occasionally in the surface, is to have lots and lots and lots and lots of salt. So, and for life as we know it, right now, life as we know it, like microbes that we bring from Earth could not survive in that with that liquid water environment. As a matter of fact, Erman is on a paper with one of our other colleagues that they just published that study that showed that water could be metastable on Mars, but life probably from Earth probably could not survive in that kind of liquid environment.
Well, this is fascinating, of course. So we have a question that sort of alludes to the future with astronauts from Satya, and she asks. We read that when astronauts arrive on Mars, they will have to build their own homes, grow their own food, and build a rocket in order to come home again. And is that true? So I'll ask that of you all.
Yeah. So it's sort of true and sort of not true. So when especially for the first mission, when the astronauts arrive there, we'll actually hopefully send some of their equipment ahead of time. So we'll send the return vehicle ahead of time. We'll send some of their equipment that can do what we call in situ resource utilization, or basically, as somebody else said, make oxygen from the surrounding environment. We'll send some of the habitats ahead of time. Now the astronauts will have to kind of assemble things and put it together, but for their initial habitat, everything will come from Earth. And same with the return vehicle. So the astronauts will have to kind of put their habitat together. They will bring some initial food and water with them from Earth, but if they're going to stay on the planet for 2 years, we can't bring everything we need to survive for 2 years with us. It would be like Battlestar Galactica sized ship to do that. So they will have to make some of their own food. They'll have to grow some of their own food, and they will have to recycle their water and potentially extract water out of the Martian surface to use to help them, grow food. And also they will have to make some of the fuel that they need to do the return. So they won't have to build the return ship, but they'll have to use some in situ technology on the planet to make the fuel to help them fuel the return ship to go back to Earth.
I'll just mention here that Jim Green, who's chief scientist at NASA now, he was very interested in the production of the movie The Martian, Andy Weir, who wrote the book, really did his research and asked around the engineering and scientific community just about what it would take, and so far as placing a story there on Mars, but actually living off the land and not having to necessarily bring your return fuel with you, but actually manufacture it there. Once again, MOXIE is the experiment that's being sent on Perseverance that will be making oxygen from the CO2 in a similar way. It's doing what plants do. It's sort of well, we and plants interact. Of course, we need oxygen, and trees take carbon dioxide. Plants take carbon dioxide and breathe out oxygen. So with this, I'd like to just, Mike has been flying around, and we see these various different landforms. I wanted to come back to Liz and just ask about the geology that we see in the Delta. We see sort of like mesas, and I'm just wondering if you could describe some of which we're seeing up close at this extreme sub-meter resolution, and also not vertically exaggerated. We're not extending a height scale. This is all rendered in real time, flying around the way we'd actually see it. So Liz, how would you characterize this delta and what we're seeing?
Sure, yeah, so there are a variety of features. It looks like Micah is going over a small crater that has active sand dunes within it. So those are, loose sands that are mobilized by the Martian winds. Of course, because the atmosphere is so thin on Mars, the Martian winds have to be extra strong to be able to move a sand grain. But then we see, you identified these mesas, Carter, and I think that's a perfect way to describe them, but they represent different time periods during this delta and when the sediments were deposited. So those lowermost mesas represent the older deposits when that delta was fairly young. And as you go up, you're going into younger and younger units through time. And actually, as we get up onto the crater rim, there are some putative, we don't know if this is true or not until we get on the ground, but there may be lake margin deposits, so sediments that were deposited at the edge of the crater lake.
Well, that is fascinating, and there's a question coming in from Ree, and she asks, how long will Perseverance have power? What happens to it when it has to power down? Of course, we lost opportunity. I mentioned that it was designed to really only go 90 days or about 3 months, and it lasted 14 years. But it was solar powered, if I've got that correct, and that Perseverance has this radio. It has plutonium. But how long? Do you know how long the rover is designed to last?
Yeah, and so the rover body for Perseverance and much of the some of the technology is very similar to Curiosity's. Herman or Kenda, you should jump in if I say anything wrong, but I think the nuclear battery is very similar to what Curiosity has. And the hope, at least, so for Curiosity, we've been up there for 8 years, going strong still, though we see a little bit of degradation in terms of power from our battery. But the hope is, lasting 10, 12, maybe 14 years with fairly nominal activity.
Well, that's very encouraging. It's exciting to have, both in the case of Curiosity and Perseverance, something that can last on that order of time. Maybe I'll ask a slightly embarrassing question for Liz. The wheels on Curiosity, they were perhaps how are the wheels on Curiosity doing? I know that was kind of a weak point of design, and that's been beefed up for Perseverance. Is that correct?
Yes, and I don't know the design of the wheels for Perseverance, but it was definitely a learning lesson for us on Curiosity. And so for those of you who don't know, our wheels, we found out not that far into our mission that when we drove over rocks, they were poking holes into our metal wheels. And so we actually had to completely revamp our style of driving and our strategic path to the mountain so that we would avoid the rockier and rubbly areas and stick to the more benign terrain so that we could prevent those holes in the wheels from getting any bigger. But since doing that, our wheels look great. There has not been very much significant wear and tear on them since we've been really careful about where we drive.
No,
But
that's
thanks,
great.
Carter.
Yeah, and I want to. We're reaching the end of our hour here, I'm just wondering. I want to ask Kenda that in the future, would you go to Mars? Hello, Kenda?
Are you asking all of us?
Well, I wanted to ask you specifically. Would you like to go to Mars? This is a question that came up.
Absolutely. I would love to go to Mars. I think it would be, it's kind of one of those final frontiers. So I would love to go to Mars.
Well, how about Liz and Herman? Would you all like to go to Mars?
Yes, I will go. Sign me up.
And Herman?
Yeah, well, I think that I'm not as enthusiastic as my colleagues here. Like I suffer from vertigo. I'm a little bit claustrophobic, but I understand that it would be super cool. But to be 7 months, enclosed in a rocket, I will leave that for Kenda and Liz.
No, no. Well, thank you, and I want to thank you all. And I'd like to know where can we see more of your work online? And that question goes to all of you.
I don't mean to answer for Armand, but since we're both at the same place, for me and Armand, you can find out more about our research at the Lunar and Planetary Institute's website, which is lpi.usra.edu. We can put that in the chat too if we need to.
Well, wonderful. And Liz?
Yeah, for me, so I work in the Astromaterials Research and Exploration Science, or ARES, ARES, division at NASA JSC, and you can find my bio there. I also have lots of papers that I've been on that you can find on Google Scholar. A lot of them are open access, so the public can read them. There aren't a lot of Liz Rampies out there, so if you just Google me, you'll find stuff.
Well, great. And also, I want to give a special shout out and thanks to the Space Science Institute and an online space games at SCIGAMES, scigames.org. And of course, if you're interested in open space and learning more about that, and if you want to download that, openspaceproject.com. So once again, for the American Museum of Natural History, this is Carter Emmart signing off and thanking you all for watching and your wonderful questions. Thanks a lot.